Um, so it's my pleasure to welcome Matt, our own graduate student here, in nilpotence theorem via homological residue fields for least superalgebra representations.
All right. Yeah, thank you, Scott, for the introduction and for organizing the seminar and for the opportunity to speak on joint work with Dan Nakano, my advisor. So I want to just start with going to the first slide. Okay, there we go. With some references. So one of the neat things I think about this project is the fact that it really kind of synthesizes a lot of work from various authors spanning several decades. And at first, it was very intense. And we've been working on this for, I think, a little bit over a year. And we're just now coming to sort of some payoff that I hope to tell you about. All right. So the first thing, I guess, to say is what is a triangulated category? Essentially, a triangulated category is an additive category where you have sort of like these exact sequences. Although they're not called that, they're called distinguished triangles. So we have an additive category with a suspension functor called the shift, which is an autoequivalence, and this class of these distinguished triangles. And then there's a long list of axioms that they satisfy. So if you have isomorphic triangles and one is distinguished, and the other one has to be as well. A triangle is distinguished sort of if and only if it's rotated, is also distinguished. For every object, this triangle x to x via the identity to 0 to the shift is distinguished. For every morphism, there's a cone, and you can form a distinguished triangle in this way, by going by f from x to y, to the cone, to the shift of x. And given two exact triangles and morphisms as depicted, let's see. Yes. Such that this were to use, you have a W from the cones to each other, and that completes this commutative square. And then this last one is pretty notorious. And if I was better at tech, I would have put in the picture, but this is called the octahedral axiom. Essentially, if you have these three triangles, then you can get a fourth one in this way. And if you draw them all out, it kind of looks like an octahedron, but I didn't do that. Okay, so for this talk, we're going to be interested in triangulated categories, but triangulated categories that have a little bit of extra structure. So we're going to be interested in what are called tensor triangulated categories. And essentially what these are triangulated categories with a monoidal product. And we're going to assume that all of our tensor triangulated categories have a unit, and that objects are exact in each variable. So these functors, blank tensor A and A tensor blank, are exact. And furthermore, we're going to assume that our tensor triangulated categories are symmetric. So A tensor B is isomorphic to B tensor A for all objects in K. So there are lots of examples of these things. The first one is if you have a scheme, then the derived category of perfect complexes over the scheme is a tensor triangulated category. If you have a field K, a positive characteristic, and you consider a group or a group scheme over K, then what's called the stable category of KG modules is also a TTC. And I'm going to say more about this later, what this actually is. Okay, So if you have a tensor triangulated category, well, you can form direct sums in your category and you can form tensor products. So the idea is to kind of treat K like a ring. And so there's this notion of a tensor ideal. So a subcategory I is called a tensor ideal if it has this absorption property. So if I tensor K lands you back in I. A tensor ideal is thick. Oh, okay, yeah. Thick means closed under direct sum. I think this came up in the talk last week. But we're going to call a thick tensor ideal prime if exactly what you think happens, if it's proper, so one's not in P. And if the tensor product of two objects lands you in P, then at least one of the two had to be in P to begin with. And the spectrum of a TTC is defined analogously to the spectrum of a commutative ring. So it's going to be the collection of prime thick tensor ideals. And we can use the spectrum called the Balmer spectrum after Paul Balmer, who first introduced it, to define a support datum on K. So essentially, for an object in K, the support is going to be those prime ideals for which A is not a member. And then you can consider these like DAs, like distinguished opens, which are the complements of the support of A, to define an open basis for a topology on the Balmer spectrum. All right. So, I mean, this opens up classification questions. Given a TTC, what are the thick tensor ideals? What are the localizing subcategories? I should say this. So a localizing subcategory is a triangulated subcategory, which is closed undertaking set in X coproducts. Yeah, so, and the thick tensor ideal, I think I already said this, is a triangulated subcategory with this absorption property. And so we'd like to classify thick tensor ideals and localizing subcategories. And in general, this is very difficult. But there are some techniques that have been developed recently that actually allow you to do this. So one approach is to take advantage of an R action, where R is a graded commutative ring. So let me tell you what I mean. So we can define the graded center of K, and we denote it this way, Z bullet K. It's a graded commutative ring, and in the degree n component, we consider natural transformations from the identity to the shift that commute with the shift up to a sign. And we say that a graded commutative ring acts on K if we have a homomorphism from R to the graded center. So in this case, we would call K an R linear triangulated category. So the technique that we're going to try to take advantage of for classifying localizing subcategories in thick tensor ideals is called stratification. So what we want to look at is an R linear TTC. What you can do is for each P in the spectrum of R, so the classical spectrum, you can construct these local cohomology functors. And these are quite abstractly constructed. So I don't really want to get into the details, but essentially they give us a way to define support in K in terms of the spectrum of R, given this R linear setup. So the R support of an object is going to be those P's in the spectrum that aren't killed by this local cohomology functor. And the R support of K is going to be those P's that don't kill the whole category. And with such a setup, so we say that K is stratified by the R action if and only if two conditions hold. So the first one is called the local global principle, which says that for every object in K, the localizing subcategory generated by X actually matches up with the localizing subcategory generated by these gamma PXs as P ranges over the spectrum. The second condition is minimality. So given an object, given a prime ideal in the support of K, we want that gamma P of K is a minimal localizing subcategory. So these P's kind of correspond to minimal localizing subcategories. And when these two things hold, we say that K is stratified.
So can you say what a localizing subcategory is?
Yeah, so a localizing subcategory is a triangulated subcategory that's closed undertaking coproducts, set index coproducts. So it's basically like you let it generate a subcategory, an object.
Why is it called localizing?
Why is it?
Because maybe that's okay, you don't know, it says that localizing is I mean, localizing it seems like the primary deal.
Yeah.
Or this thing generated by the dome, so that like being thick, instead of supposed to press something and the other so that we go anyway, that's okay, so that's fine.
Yeah, I guess I don't really have a good answer or the terminology.
Hey, John, do you have a good answer?
Yeah, basically, it's you can factor it out. I mean, what a fixed subcategory is a fixed subcategory because you can factor it out. You're actually localizing at the prime. I mean, you're localizing the harm.
Okay.
And this is the same sort of thing. I'm not sure exactly how that works, but that's the same sort of thing.
Okay, all right. Okay, anyway, so yeah, I was gonna just say this. In general, if you want to show that a TTC is stratified by an R action, it's the second condition that's the hard part. To my knowledge, the last I looked, there aren't any examples where the local global principle fails to hold. Okay, so why is this useful?
Back up once, I'm sorry.
Yeah, I'll go back.
So I've forgotten what this gamma P is something that you found like in Hartshorne's book, but I can't remember what it is. So could you say what it is? I just forgot the definition.
Okay, in Hartshorne's book, I don't know what they're talking about. In this case, so it's basically, there's this whole theory of localization functors. And yeah, I'm not sure if I really want to get into it exactly.
Some of the sections which are supported on
Yeah.
This is fun years and that. So
But the support is just P itself or zero, depending on the time. So it was introduced by John and Dave and Jeremy.
Well, we did it. We did it.
Correct. But the idea came from
Yeah. But
real work.
the gamma P is of X is a different element of K. So to start with an element of K, what is I'm just writing some, I mean, what could I think of gamma P of X? I mean, X is some element of K. Is there a way to think of like what gamma P X is supposed to be?
I think so. The embedding of localizing subcategories in adjoint, and basically you first the adjoint within the embedding, which is function of the case itself.
I was just like, we can way to think of what gamma P, what does gamma P do to an element of X? Like, is there just a way to think about it?
So I think I'm not sure.
That's fair, I'm saying.
So normally, when you do the support, you get something like a finite dimensional object, you get something which is a close subline. But this gamma p is some like huge infinite dimensional object that you construct. It's a specialization functions. And it's just supported at p raised to.
So now you're showing all the parts that the concept is.
That's right. That's exactly.
When you do this in group algebras and things like that, and I think also in the group theory, there was actually a module. If you're talking about a module category, then you're tensoring the, that's what it does is it sort of kills all of the support that's outside of P.
Okay, yeah. So sorry, that was probably not satisfying.
That's okay, that's pretty.
Okay, but anyway, so let me say why stratification is useful. So it answers the questions. So if it doesn't answer those questions. It answers the questions from before, these classification questions. So if you have an R linear TTC stratified by that action of R, then you get these bijections between the localizing subcategories of K and subsets of the R support. And furthermore, if K is stratified in no theorem, then you actually get a classification of the big tensor ideals as well. Big tensor ideals in the compact part of K. Between fixed subcategories of compact objects and specialization closed sets. So for localizing subcategories, you look at arbitrary subsets of the R support of K. For the big tensor ideals, you look at specialization closed. Okay, so I have some examples where this is actually known to hold. So if you consider the big stable module category of KG modules, this is a TTC, and it's actually stratified by its canonical action via the cohomology ring. So we get bijections here between the localizing subcategories and the subsets of the proj of the cohomology ring. And the way that you actually prove stratification in this setting involves a lot of changes of categories. But I will say that the proof is greatly simplified if you want to just consider an elementary abelian 2 group. And that's going to come into play later on for what we did. Okay, now I'm going to kind of shift gears somewhat entirely and talk about a category theoretic notion. So I want to tell you about homological primes. So there's a way to construct an abelian category given a TTC, and it's called the module category. And what it is, let me see if I can move the window. So this category I'll call A, or denote with mod K, has this object's additive functors from the opposite category of K to abelian groups. And the morphisms, of course, are natural transformations between functors. And this module category sort of receives K via the Onetta embedding that I call H here. And something important to note is actually you can put a tensor product on this module category via something called day convolution, which is right exact and which makes the Onetta embedding a tensor functor. And you can look at the compact objects, this tensor subcategory of compact objects, which I call AC or little mod K. It's something called the frayed envelope of K, which means you can kind of look at a restricted Onetta functor from K to mod K, and it's sort of the universal homological functor out of K, which means if you have a functor which sends exact triangles to exact sequences, then it has to factor sort of through little mod K. Okay, so I'm telling you about this because we can actually define another notion of spectrum for tensor triangulated categories by looking at this module category. So the homological spectrum, which we call or denote SPC H of K, is going to be maximal stair tensor ideals in mod K. And you can actually use this to give another support data on K. So of course, this is a topological space with basis of closed sets given the way you would expect those maximal stair ideals for which X hat is not a member. Remember, X hat is the image of X under the omega embedding. And this gives us support data. And so one of the things Balmer showed in his original 2005 paper is that there's a unique continuous map from the homological spectrum to the categorical spectrum or the Balmer spectrum called phi. And this map phi is often referred to as the comparison map. And one thing that's known about it is it's always surjective as long as K is rigid, which means that it admits duals. But there are many examples actually where this map is actually a bijection. And that led to this conjecture called the nerves of steel conjecture, which is kind of exactly what I just said. So the conjecture is that this comparison map is a bijection for every tensor triangulated category. And if you ever read any of Balmer's papers, it won't be too long before you kind of run into some lively language or analogy or something. So I pulled this screen cap from the paper. So he says, in view of the avalanche of examples where the comparison map is a bijection, it takes nerves of steel not to conjecture that this property holds for all TTCs. So here's the avalanche. And I put a couple of examples here. There are more, and we're going to get to some more in a second. So if you have a quasi-compact, quasi-separated scheme, then this derived category of perfect complexes fulfills nerves of steel. And similarly, for a finite group, the small stable module category exhibits this property as well. Okay, so the reason I think that these homological primes, these maximal stair tensor ideal subcategories, were introduced in the first place was for stating abstract nilpotence theorems in tensor triangulated categories. So given a homological prime, so an element of SPCH of K, Balmer defines this thing called a homological residue field, which is the composition of Yonetta with the Gabriel quotient by the localizing subcategory generated by B. And the theorem is that if you have a rigidly compactly generated big tensor triangulated category with compact part K, taking a morphism in F from X to Y, where we're going to say X is compact and Y can be arbitrary. If this morphism actually vanishes for all of the homological residue fields, then that morphism is tensor nilpotent. Okay? In T. All right. So now I want to talk about Lie superalgebras, which feels much more down to earth to me. So a Lie superalgebra is like the Z2 braided analog of a Lie algebra. So it has this Z2 grading, so you can decompose G equals G0 plus G1. And you have a bracket called the Lie super bracket, which kind of satisfies Z2 graded analogs of usual Lie algebra axioms. So we have super skew symmetry. So X bracket Y is Y bracket X up to a sign determined by the degree of X and Y. So X and Y here are pure, and then to do arbitrary elements, you just extend linearly. And then the super Jacobi identity, which looks like the usual Jacobi identity, but again, you have to include these signs. So I put an example here. So if you've ever seen Lie superalgebras before, probably the first example that you saw was GLMN, this type A situation. So GLMN is the Lie superalgebra whose elements consist of these m plus n by m plus n matrices, and they kind of have this block form. I don't know if it's actually right to call this block form, but you want to think of like the four quadrants kind of separately. And the bracket is kind of given as follows. So if A or B is even, then it's the usual commutator. If A and B are both odd, then you actually have to add A, B plus BA. So for classical Lie superalgebras, and I think I say what classical means in a second, but I'll kind of just say it now. It means that you have a connected reductive algebraic group where when you take Lie of big G, you actually get little g0. Okay, g0 is actually a Lie superalgebra in its own right if you just restrict the bracket. But anyway, so if you have a classical Lie superalgebra that admits something called a stable action of g0 on g1, you can take a generic point and look at the stabilizer in this way, and then the g0 normalizer of the stabilizer, and you kind of get an isomorphism between the cohomology rings HG, G0 and HF, F0 up to the end, where you set F, which is a Lie sub superalgebra, so it has this even odd decomposition, where F1 is the H invariant part of G1, and F0 is the bracket of F1 with itself. And if we let R be the cohomology ring, then both Kujawa and Nakano actually showed in their paper also that the relative F0 cohomology is isomorphic to the symmetric algebra star. Okay. So I have this slide here where I just kind of remind you what a representation of a Lie superalgebra is, but given the time, I think I'll go through this a little bit quickly. So essentially, given a Lie superalgebra, you can form the tensor algebra, you can quotient out by this ideal to get the universal enveloping superalgebra, and this is a superalgebra in the normal sense. And representation is the same thing as a UG supermodule. So this is like an ordinary module, although you have this grading, and the action of G has to respect the grading. So it's just introducing this Z2 grading to the situation. Okay, so let me tell you about the stable categories for the superalgebra representations. So I would let this CGG0 be the category of G supermodules, but I'll abbreviate to modules, which are finitely semi-simple over G0. And I let the F GG0 be the finite dimensional modules in CGG0. And it turns out that these categories have enough projective and injective objects, and actually these projectives and injectives coincide. And so they're Frobenius categories, and we can form what's called the stable category, where the objects, for example, in stage CGG0 are the same as those of CGG0, but there's a relation on morphisms. So two morphisms are equivalent in the stable category if they're difference factors through a projective. So this kind of has the effect of killing all the projectives, making them only zero. And so this big stable category is CGG0. So it's the fact that it's a compactly generated tensor triangulated category. And the full subcategory of compact objects is just this little stable module category on F, GG0. All right. So what we were able to do was actually use the ideas of that theorem on stratification for elementary abelian 2 groups to get a result similar for the detecting subalgebras. So if F equals F0 plus F1 is any detecting subalgebra, what we were able to show was that the TTC big stage CF F0 is actually stratified by the action of the relative cohomology ring, which from a couple slides ago is the symmetric algebra on F1 star. And so we have the corollaries that come from the consequences of stratification. So we know that thick tensor ideals in case C are in bijective correspondence with specialization flow sets of the projectivized cohomology ring. And actually, I wrote it as a corollary, but it's not clear why just from what I've told you. But it turns out that it actually verifies nerves of steel in this setting. So the comparison map between the homological spectrum and the Balmer spectrum is a bijection. So more evidence.
So you may want to mention that corollary was actually an open problem.
Yes, yeah.
Right. That was in our paper back in 2017.
I think the open problem was the stratification.
That's right.
Right.
That's right. Sorry, the theorem.
Yes.
Yeah, we proved the corollary.
The corollary was known before.
That's right.
This is a new way to do it.
Yeah.
Okay. All right. So I want to go back to thinking about homological primes. So remember, they're very sort of abstractly defined. But it turns out by some work of Balmer Cameron, we actually have some methods for constructing homological primes. And what it boils down to is you need to have a tensor functor from the triangulated category that you're interested in to something called a tensor triangulated field. So a tensor triangulated field, this is kind of terminology introduced in Balmer's papers, but you should kind of think of them as like ordinary fields in commutative algebra. So they don't admit like non-trivial localizations. But anyway, maybe this diagram isn't the most transparent thing to look at first, but the idea is given one of these tensor functors to a TT field, you feed it to the diagram and it produces for you a homological prime. So the question is, how do we get these tensor functors to fields? If we find a natural class, then we get a natural corresponding collection of homological primes, and by extension, homological residue fields. Sure.
What do you mean by big tensor triangle?
Yeah, so a big TTC, okay, so you should kind of think of it as like having, like, in the example of the stable categories, the big stable category had infinite dimensional modules. The small one only had finite dimensional. But the big one was sort of generated by the small one by taking direct sums and so forth. So
And then, okay, so the goal is to construct the functors from the big TCC to the tensor triangulated field of F,
yeah,
and will different functors give you different homological primes? How much control do you have over that? Or
yeah. So I'm going to talk about this in a second. I guess in principle, different functors could give you different.
could it be the same?
I guess different functors could give you the same one.
If they're the same orbit, for example.
Right, exactly. So, yes. Okay, so what I want to talk about now is actually a way to construct the homological primes for GLMN. So, a theorem of Bokujawa and Nakano is if you consider GLMN in the detecting subalgebra F, there's actually a homeomorphism between the end proj of the symmetric algebra on F1 star and the Balmer spectrum of the small stable module category of FGG0. But on the other hand, if you consider an X in F1, any element in F1, and look at the Lie sub superalgebra generated by that element, you can kind of consider this big stable module category on X0. And it turns out that this is actually a TT field. And so these natural restriction functors are perfect candidates for feeding to the diagram on the last slide. So we kind of get a collection of homological primes indexed by elements of F1 in this way. So we kind of get two collections. So I guess I call this F prime to be those homological primes that we get by restricting from F, and then F without a prime is those homological primes that we get by restricting from G. So you can kind of look at both situations. And this is the corollary that I had before. From stratification, coupled with some other work of Balmer, we actually get kind of for free that this first inclusion is an equality. So we actually get all the homological primes, but we already knew that because we just said that nerves of steel held. But what we wanted to do was kind of see if the second collection contained all the homological primes. I mean, that would be the next thing. And so that's what we were actually able to do by looking at nilpotence. So there's this theorem of Balmer, I should have put credit here, that if you have a big TTC compactly generated, and a family of points of the homological spectrum, such that the corresponding homological residue fields collectively detect tensor nilpotence. So you're kind of going the other way. So I have a collection of homological residue fields. If you show that it detects tensor nilpotence, then that collection actually had to have all the homological residue fields. So we kind of stared at this for a while. And so I kind of want to let KG, just to shorten things up, be the big stable category of GG0 representations, and KF to be the stable category of F of 0 representations, the big categories. So here's kind of the theorem that we were able to show that kind of combines everything. So first of all, I mean, okay, if you look at H bar B of X. So this is the homological prime corresponding to an element X when you consider restriction from the G. If that is 0, then of course the restriction of F, when you hit it with that homological prime that you get when you restrict from the F, that same X is going to be 0. So that's not actually too hard. But the second thing that we were able to show is that if H bar B prime of X of the restriction of F is 0 for all X in F1, then actually restriction of F had to be tensor nilpotent. So that's kind of directly applying Balmer's nilpotence theorem in our setting. The new part, and the part that was kind of the hardest part, was showing that a morphism is tensor nilpotent in Kg if and only if its restriction is tensor nilpotent in Kf. And so we were able to use that result combined with the fact that this collection of homological primes for the stable category of GG0 representations is n-invariant to show that the comparison map is a bijection. So we actually classify the homological residue fields for stab C GG0. And so the nerves of steel conjecture lives on, and we kind of supplied some more evidence for it. So I think I'll stop here. Thank you.
Thanks for the speaker.
Once you think your process can be sent to other places.
Yeah, of course. So I mean, that's what we're thinking about now. Yeah, and then we're pretty optimistic.
Any questions? If not, let's thank the speaker again.